Okay guys, so regarding the doubts you guys have, so there are two concepts we follow in probability. One is called with replacement and one is called without replacement. So with replacement is when you select more than one items, but as soon as you select one item you put it back, then you again select the second item and then you put it back. That is, we are replacing back. Without replacement is when, if you have to select more than one item, you just keep it. You do not give it back. So a very good example would be, let's say there is a bag. Let's say there is a bag which has got 3 red balls, 3 blue balls. Now you are asked to find out the probability of 2 red balls. Now given the fact, and the same question can be asked in both the scenarios. So first of all, we'll focus on with replacement. Now 3 red balls, 3 blue balls. You're asked to draw 2 red balls. What is the probability of me getting 2 red balls? So in the very first draw, the probability is half. So what I'll do, in order to have a different dot, I'll see 3 red balls and 4 blue balls. So the probability of drawing a red ball is 3/7, and probability of drawing a blue ball is 4/7. That's straightforward. Now we have to make 2 draws. So in the first draw, and that is with replacement, so in the first draw the probability of getting a red ball is 3/7, and means multiply, and in second draw the probability of getting a red ball. So see, in second draw also the bag remains in the same state what it had before first drawing. So when before first drawing it had total 7 balls, 3 red, 3 blue. After drawing and with replacement means the ball which you drew is again back into the bag. That means the bag after the first draw again has the same quantity. So the probability of drawing the red ball doesn't change. It is still 3/7, which makes it 9/49. So that's the probability of drawing 2 red balls. Now same question here without replacement, which means as soon as you draw the first ball, 3/7, right? But you do not put it back. Now when you do not put it back in the second draw, think of second draw as a totally different attempt in which you just have 2 red balls left because there were 3, one you already draw. So there is two red balls left and 4 blue balls. So now the probability of extracting a red ball from the blue ball is 2/6. There are 6 balls left, so 2/6, which makes it 5. Okay guys, so this is 3, okay, 3 to 6, 6/42, and after calculating it came out to be, let's say, 0.13, let's say. So if you see, when you draw a ball without replacement, the probability of drawing it becomes less there rather than with replacement. Isn't that obvious? Because after second drawing, the total number of balls decrease and your sample further on decrease. It's not like, so we all know 1 over let's say 3/4, 2/3, 1/2. 3/4 is 0.75, 2/3 is 0.66, 1/2 is 0.5. So we keep on decreasing things, the net always decreases further on. It's not like it is going to remain same. So likewise, 2/6 into 1/5, the probability keeps on decreasing in case of without replacement, that's obvious. And in with replacement, the probability also decreases, but it doesn't decrease. The slope of a with replacement, if I have to plot a point for with replacement, first attempt, second attempt, third attempt, this is going to be like this. And this is your number of attempt, first, second, third, and this is your probability. What I just created is a probability density function. On the contrary, if I'm going to do this on the first attempt, it is going to be this and this will be same, because when you draw the very first ball, may it be a without replacement, may it be a with replacement, for very first ball the probability will still be same. For second ball it decreased, for third ball it further on decreased. That's the difference between with replacement and without replacement. The cumulative probability density function, this is cumulative. If you have to calculate this is cumulative probability density function. This, anyone can tell this area is more because this area is basically this, right? Okay, so I hope you are now clear with without replacement and with replacement. So I hope you are clear till here. Now coming on to people getting confused in where to use binomial distribution and where to use basic probability. Actually, there is no scenario which you can calculate using binomial distribution, but you cannot calculate using probability. So if you remember, in binomial distribution, the only condition was that two events are mutually independent. Now, when you say two events mutually independent, that means that there is no way that the probability of same event happening second time or the probability of second event is dependent upon probability of first event. Doesn't it sound similar to with replacement? Right? In with replacement also, our second draw didn't depend upon first because we were replacing. So binomial distribution is specifically for mutually independent events. Hence, whatever we calculate in binomial distribution, which is NCK, probability of happening and probability of not happening, is mutually exclusive events, mutually independent events. On the contrary, binomial distribution for without replacement. Okay guys, so by now I explained you the binomial distribution, why we use it in with replacement, because that is what it is meant to be, two events mutually independent. Now if two events are mutually dependent, that distribution is not called binomial distribution, it is called hypergeometric distribution. Geometric distribution. So what happens in hypergeometric distribution? I am going to take the same example of here. So here in case of with replacement, 3 red balls, 4 blue balls, and we have to extract 2 red balls, it would be x equals to NCK, which is 7C2, probability of extracting red ball 3 by 7 square over 4 by 7 raised to the power 5. This was the binomial distribution of this event. Now if we have to calculate the probability of extracting 2 balls in without replacement, we have to basically go to a different distribution which is called hypergeometric distribution. And the way we come here is basically think of it like conditional probability. What you're supposed to do, there are 7 total balls in which we have to extract 2 balls. So total number of favorable events is, total number of possible events is 7C2. That's straightforward because that's how the general probability works. Total number of events over favorable events. Now favorable events is we have to select 2 balls out of 3 balls, right? 2 balls out of 3 balls and 0 balls out of 4 balls, which is the blue ball. So 3C2 into 4C0 over 7C2. That is okay guys. So by now we calculated that the probability distribution of drawing 2 red balls in case of with replacement and in case of without replacement. So in case of with replacement, that was our binomial distribution, which is nothing but binomial distribution, which is nothing but hypergeometric distribution. So that is 7c2 3 over 7 square 4 over 7 5, where just to give a context of the problem was there is a bag which has 7 balls, 3 being red, 4 being blue, and we have to find out probability distribution for 2 red balls. Here we simply did 3c2, 4c0, 7c2, where 7c2 was total number of ways in which we can draw 2 balls, and 3c2 and 4c0 is ways in which we can draw without replacement, right? Now we know the formula for this one. The formula for this one was NCK probability, the success probability raised to the power of k, into 1 minus probability, which is the unsuccessful probability raised to the power n minus k. So the generalized pattern here would be NCK. P is the success of probability raised to the power k, and this is 1 minus p raised to the power n minus k. In this case, this is a bit tricky case if we have to create a generalization. So for example, I'll try to use these terms, but there would be a couple of terms added. So we know that n here in this case is 7, right? And also what we know is x is the total number of unfavorable items. So in this case, x is basically 4. So n minus x is what? N minus x is total number of favorable items. I'm not saying outcomes, I'm saying favorable items, because outcomes I'll come on to next. This is small x, which we generally ask x is equal to 2, right? So this small x is number of favorable outcomes, right? This is what we want out of favorable items, which is n minus x. Okay guys, so we were deriving this formula. So all we have to do, just put in these values and we'll get a proper derivation, which is n minus x c small x, which is nothing but n minus 4, which is 3 c 2 x c. Okay, so here is the thing. So number of favorable outcome is x, which may be equal to let's say which may be equal to 2 events, 3 events, 4 events, etc. So let's say when I say 2 events, 3 events, let's say the question would have been 1 red and 1 blue. In that case, the formula would have gone 3c1 into 4c1. So we can take one of the event as a, which is 1. So second event x minus a becomes automatically x minus a. So that way all we have to do is n minus x c a. I'm going to replace it like this. So second event becomes automatically x minus a, where x is total number of favorable events, a being one of those events which happen to belong to the second party, which is n minus x over n c x. That's the formula for probability distribution in case of without replacement, and this is with replacement. Binomial distribution, this is hypergeometric distribution. Now coming on to the problems. Let's see. Problem was a shopkeeper has 50 pair of shoes. It was specifically mentioned in that problem that he brings the shoes out and put it back. Now what happens is he takes 3 pairs in one go. 3 pairs in one go. Now 3 pairs in one go doesn't mean he has 3 hands. It simply means that he's just pulling out 3 shoes without checking which one he put, which one he pulled. Because let's say if he picks out pulls out one pair of shoe, opens and checks it. Now he knows how many are left in there and how many, and that's how the probability changes, because now he knows how many of the kind are left in there. What if he simply took one box out, then second and third without checking? Because in that case, the probability of all 3 boxes would be same, because he doesn't know what happened. So 3 pair of shoes, right? And he is taking 3 pair of shoes out and putting it back, which means this is a okay, guys. So yeah, continuing from where I left, there is a shop with 50 pair of shoes where he's pulling 3 pairs out at one time, and then we know that there are 7 pairs which are defective. What in question they have asked the expected value. Forget about expected value, that's different concept. I'm going to calculate the probability distribution, just keeping it simple first. Then I am going to come on to why expected value and how is it different from probability distribution. So the probability distribution of the guy watching or getting a defective pair of shoe in a sample of 3 is at least 1, I would say, in 3. So what are the possibilities in a sample of 3? In a sample of 3, either he doesn't get any defective, either he gets 1, either he gets 2, or either he gets 3. They are asking him the probability of the part where he gets either of the pair as defective, which means what they're asking is px1 plus px2 plus px3, right? This is what they're asking. We know anyways there are 4 items, so what I can do is I can simply write 1 minus px0, which is where px0 is the probability that in that particular sample, all the pairs are good, none of them is defective. So px0 is nc0, which is 3c0, probability of pulling out a defective pair, which was 7 over 50, which is becoming 0, and 43 over 50 raised to the power of 3 minus 0, which is 3. And the effective probability of getting a defective pair is 1 minus px0. You can do the calculation part yourself. This is what the probability of defective item in case he's replacing each pair. He's in case he's pulling out 3 pairs, right? With replacing. Now, same question, a shop with 50 pair of shoes where 7 are defective. He's pulling out 3 pairs, right? But he is not replacing them. When I say he's not replacing them, or means he's checking them in this case, means that the 3 pair of shoes, the probability of getting the first pair of shoe as defective is 7 over 50, and the other two, the probability changes, it would be 49, because that's what we do in without replacement. This decreases. So 49, 7 over 50, and then 49, and we know 43 are the ones which are in good shape. So 43 over 49 into 42 over 49, 48, sorry, right? This is px is equal to 1. Now, if I try to put this formula just to verify whatever we did aligns with this formula, it is for x equals to 1, which is a. So here A equals to 1. Okay guys, quick thing. This is not 0, this would be 2 because there are in all 3 pairs. So 1 goes to favorable, 2 goes to non-favorable, and in all 7C3. 7C1 into 43C2 over 7C3, which is nothing. 7C1 is what? 7, right? 43C2 is what? Factorial 43 over factorial 41 factorial 2, right? And 7C3, sorry, not 7, it would be 50C3. So 50C3, I'm going to take it to a new page so that you guys understand. The probability of getting one piece defective out of 50 in a 3-pair trial, which doesn't matter because now that you're replacing, is 50 C3. That is total ways in which you can select those three samples, out of which 57 C1 cross what is left 43 and what is left 2. Just to quick check, whatever you're doing is fine. 1 plus 2 equals to 3. 7 plus 43 is equal to 50. That way you make sure that you have not taken anything which is not required. Now this is 7C1 is factorial 7 over factorial 6. Again 7 cross 43C2 is factorial 43. I'll solve this here so that it's 43 over factorial 41 over 2, which makes it 43 into 42 over 2, correct? So 43 2 over 2. 50C3 is factorial 50 over factorial 3 factorial 47, which makes it 50 into 49 48 over 3 into 2, right? And if I put this into this formula, it makes it 7 into 43 into 42 over 50 into 49 into 48 into 3. How come this 3? Like, I have to substitute this 2 and 2, so it's 2 into 3 over 2. That's how 3. Now if you see, we didn't take this into attention. So while we were deriving the probability here, we should have done into 3 as well. Why we would do into 3 as well? This is the probability when he draws the red ball in the very first attempt here itself. How about the order changes? This can happen in 3 ways. Into 3 different ways this can happen. This can happen if this goes here and this goes here, and this can happen if this red ball he gets it here, because the denominator is changing. Now you will ask me, then the values would also change, like 7. How come this? Then I'm going to prove you right now. So in px1, which is, let's say the red ball comes in second attempt. So in first attempt we got a blue ball, in second attempt we got a red ball, in third attempt we got a blue ball. You again see that denominator is same and the numerator is just juggled up. That's why they've straight away multiplied into 3, because these things are going to just simply juggle up and still the product would be same. So that's why the hypergeometric distribution with the formula of getting at least 1 is this one. Then 2, likewise we are going to apply the formula here, and 3. So in spite of doing that, what we can do the same thing which we did in earlier, which is 1 minus px is equal to 0, which is 1 minus, again when everything is fine, that is what it is asking, like, So 2 red balls, that means not 2 red balls, it is the no defective piece. No defective piece means 7C0. All full sample is collected from effective, which is 43C7 over 50C7. Just double checking. 7 is equal to 7 plus 0. 50 is equal to 43 plus 7. This is the probability which would come of the same question in case he would be doing it without replacement. Right? Now, the solution to the same question where it was 50 pair of shoes, 7 defective, and the probability of not getting any defective. I told you here in this case with the formula as well, and when without formula. Here I told you with the binomial theorem, the case in which they find probability with the help of binomial theorem. Now here the question goes furthermore. They are asking the expected count of the defective shoe. Now expected count of defective shoe versus probability of defective shoe are two totally different terms. Probability of defective shoe would always be less than 1, while the expected count, now count can be anything, but it would always be less than 7. The expected count of defective shoe would always be less than 7. Has there been the question that what is the expected count of non-defective shoes? In that case, that expected count would always be less than 43. The generic formula for expected count is NP, where P is the probability and N is the number of items satisfying that probability. That's how we get the expected count. Now, to the question that why aren't they using binomial distribution to find the expected count? They are using binomial distribution. It's Px. I would say Px is equal to Px, which is greater than equal to 1. That is what they are saying in case of defective shoes, 1 and for all. So which is equal to Px1 plus Px2 plus Px3. Now to find the expected count, this was the probability distribution to find the expected probability. Now to find the expected count. Now in this case, if we multiply this by the count of shoes which would be satisfying this particular probability, which is 1 multiplied by Px1 plus 2 multiplied by Px2 plus 3 multiplied by Px3. It is nothing but the weighted average. So see, Px, this part will always be less than 1. But when you multiply this by 2, 3, there are chances that it would be more than 1. For some cases, may not be for this question. Now why we are multiplying with 1, 2 and 3 to get an expected value? That's pretty straightforward. For example, there is a bag where there is a red ball and a blue ball. I would say 2 red balls, 3 blue balls. Now when I take 2 red balls and 3 blue balls and they are asking me that you have to draw 2 red balls, what is the expected? Means they are asking me at any point of time what is the count of red ball which you will be able to draw every time, which is basically Px is equal to 2 multiplied by 2. Now Px is equal to 2 in this case is 5C2, 2 over 5 square into 3 over 5 cube whole multiplied by 2. Now this is I'll solve this thing for you so that you guys don't. So it will be 5 into 4 over 2 into 2 into 2 into 3. 3 is 9, 3 is 27 to 5 to the power 5. 2, 2, 2. Okay. So it becomes 5, 4, 20, 40, 80, 80 into 27 over 5 raised to the power 5. So just calculating on a calculator, which is 80 into 27, 2160 divided by is equals to this answer divided by 5 raised to the power of 5. 0.6912, it is not the probability. This actually means that whenever you are going to do this part, drawing 2 red balls out of a bag of 2 red balls and 3 blue balls, there you will always have 0.6912 red balls in your hand after doing this, which looks very unrealistic. How come it's not a whole number? But that's how it works, because if I'll ask, so if I do this 20 red balls, 30 blue balls, and you are asked to do multiplied by 20, in that case I'm going to multiply, this is going to be 20 over 50, 0 0 cancel, this is only 30 over 50, 0 0 cancel, but I'm going to multiply it by 20 because 20 red balls. In that case this would be multiplied by 10, which makes it 6.9. Now this makes sense. There is a very good chance that you will have 7 total red balls anytime if you are drawing 20 red balls out of this. So this is expected value. This is called expected value, and probability is without multiplying this. Probability is basically 7 over 20. Just a rounded off probability. That's the probability of getting 2 red balls. So probability and expected value are two totally different things. Now there is a question which says that you are given a list of elements, let's say 1 2 3 4 5 6 6 6 6 7 7 7, and then you are asked to randomly select 3 elements. They are not telling that you have to select 3 elements all at once. They're saying select 1, then select 1, then select 1. They are not mentioning anything about putting it back. So when they are not mentioning anything about putting it back, most of the time that means that you are not putting it back. You are the 2, the 3 or whatever events, they are not mutually exclusive. So they are saying that you pick 3 numbers randomly, select 3 numbers randomly, and then what is the probability that you get a 6 as one of those numbers, right? Now the probability of getting at least 1 6 out of those number is equal to 1 minus probability of getting no 6. Isn't that right or not? Now probability of getting no 6 will go with basic probability thing, which is 1 minus the probability of getting no 6 in 3 attempts is, we have got total 12 and 6 there were 4, so no 6 is 8 over 12 in the very first attempt. What we are left with is 11, right? And what we are left with is 7 into 6 by 10. That's how we do. We decrease the count, and we're decreasing the count here as well because that's what is left. Now I'll come to that formula. Now as per that formula, which I already told, which is hypergeometric distribution in case of without replacing. What is that? So that would make it, we have 8 elements, so 8 C 3. Rest of the 4, which is 6, we are not drawing any, which is 1 minus. and then 8 for 12, 12C3. Also same mistake which I did earlier. This is when I'm getting one here, one here, one here. The order doesn't matter. No one asked me why we are not multiplying it by 3 or why we are. So let's go to this first. This will answer it. 1 minus factorial. So this is basically 8 into 7 into 6. 7 into 6 over 3 into 2. And this is 12 into 11 into 10 over 3 into 2. You see, I didn't multiply it by 3, which was not required. And there it was required. What is going on? Some sort of rubbish? No. Basically, this is a combination. Here, what number you are picking? Okay, guys. So, we were discussing about when we take a general probability like 8 by 12 into 7 by 11 into 6 by 10. Why didn't we multiply these? So the generic formula of rearranging the terms is, for example, we have 3 red balls. Factorial n over factorial of the term, factorial of the number of times the term is repeating. So here it is 3 and n is also 3. So that is why factorial 3 over factorial 3 makes it 1. For example, had this been the case, RGR means 1 red ball, 1 green ball, 1 red ball. In that case, factorial 3 over factorial 2. That means there are 3 ways to do this, which is RGG, RGR, RRG, and GRR. Now, why 3? Because if we are going to take factorial 3, which is factorial 3, by the way, this you guys should all know that the ways in which n items can be arranged is factorial n. Now factorial 3 is 6. What that will do is, this is what it's going to do. RGR. This is, let's say, R1 and R2 and R2 and R1. It is going to treat these two as two different. But in actual, we are not differentiating because order doesn't matter. So that is why it's 3. Similarly, had there been like a case, something like 2 red balls, 2 green balls, 1 blue ball. In that case, it would be factorial 5 over factorial 2 into factorial 2. That way, we get factorial 5 over factorial 2, which is 5 into 3 into 2, which is 30. There are 30 ways in which we can rearrange it. Okay. So, that is why here we are not multiplying it by 3 because all these 3 are of single type. This is, when I say single type means, let's say this is the probability, this is non-repeating thing. 1, 2, and 4. Likewise. Okay. So I guess that should be it. Even if you let me know if you need something else, but this is how we choose to multiply in case we are deriving a conditional probability. In formula, which is the formula for this is 4C1 plus 4C1 into 8C0 into 8C2 over 12C3 plus 4C2 into 8C1 over 12C3 plus 4C3 into 8C0 over 12C3. This formula takes care automatically of this thing, that what number we need to multiply to rearrange the output within itself. So that should be it, guys. Thank you, and let me know if you have any doubt or if you feel something is wrong.